try it. Okay, cool. Okay, Mike. Looks like we have Carr. Hey, Carr. Welcome. It's good to see you. Mike, now I feel like we should have some giveaway prizes. Now I'm disappointed that I don't have swag. Next time, guys, we'll have some swag. And the last group did get their books. I made sure.
Oh, brilliant.
Yeah, that was fun. Okay, cool, Mike. There'll be some more people that will drop in, but I will let you go ahead and take it away and set it up.
All right. Well, thank you, everybody that's joining the Cloud Native at Scale meetup today. We've got an exciting topic, leveraging cloud native key value stores to build hyperscale infrastructure. We have two amazing speakers today, Ishian and Charles. They're going to talk about a couple various points, just some quick updates. What we had as a takeaway coming out of 2021 at KubeCon was that the adoption rates were increasing massively, and they're moving into markets that weren't traditionally early adopters or on the bleeding edge, because we all know the bleeding edge is where people bleed. So big finance, big regulated companies, whether it's fintech or other tech-like firms that aren't maybe the San Francisco proper tech companies, are adopting Kubernetes. And there's a higher demand for higher order tools, developer experience driven tools, and hyperscale, so large scale. So how can companies and or industries adopt Kubernetes and layer them onto the required scale that they've already built to help, realize the fundamentals and guarantees and possibilities with a more cloud native infrastructure, something a little bit more portable like containers and Kubernetes. So with that, I'd like to introduce our speakers today. Ishian's going to go first. He is a maintainer of KubeBrain and a senior software engineer at TikTok. Everybody loves TikTok. My daughter thinks like I'm talking to the Messiah here because I'm talking to somebody from TikTok today. She's 13 years old. Besides this, so he's on the cloud native team at TikTok. He also has a deep understanding of workload deployments, extensive experience in multi-cloud applications, and he is a tech lead who has designed and implemented the first generation of TikTok's cloud federation platform, managing hundreds of Kubernetes clusters across the data center and around the world. TikTok is popular, if anybody hadn't noticed. Charles is currently a senior engineer at PingCAP on their cloud services team. He has more than 5 years of experience in computer resource scheduling, performance optimization, containerization. He's a huge open source advocate and maintainer of several open source projects. Some of them include Kubernetes Virtual Cluster, yay, clusters and clusters, love it. OpenYurt, CloudWAF, and we are going to hear from both of these exciting individuals today. So with that, you didn't come here to hear me talk, but I'm just going to say quickly a little bit about me. Mike Bowen, I work for BlackRock. I'm a senior principal engineer and super excited to be given the MC reins from Josh yet again. And with that, Ishian, the floor is yours.
Okay, can I share my screen?
You should be able to. Yep.
Yeah. Can you see the slides?
We can.
Yeah, cool. And okay, hi everyone. This is Isha. And today I'm gonna introduce KubeBrain to all the fields. KubeBrain is a high-performance key-value storage for Kubernetes, and this is the agenda today. And we have 4 chapters for this slide. The first one is the background, and we will talk about why we try to design the KubeBrain, what's the problem we encountered, and the second one is the system design, how we design KubeBrain, and the third one is some performance data, some practice we do in TikTok, and the last but not least is some future of work, what we're going to do in the next few months. Okay, cool. And let's get started. And in TikTok, we have a increasing business, so we have to face the massive scalability problem. We have several hundreds of clusters to manage and like hundreds of thousands server to handle. So we have a massive scalability problem. And application running on Kubernetes are diverse. For example, for products that is divided into the following 4 categories. Microservice for API, big data for data analysis and processing, storage for users' video and data, and machine learning for AI models. And to facing the scalability problem, we have two ways to go. The first one is horizontal multi-class. We will horizontal scale our clusters, which leads to multi-clusters. That's what I have done and designed in TikTok. And another way is vertical scale. We will like build a huge single cluster. And after the work we done in TikTok, we summarize some pros why we make a huge single cluster in Badan. And the advantage to build a huge cluster is to reduce the management costs and reduce the resource fragmentation and it helps us to improve the utilization. And as we all know, Kubernetes is a centralized architectural system. All the components interact with each other through the API server. The API server provides front end to all the components in Kubernetes, right? And the API server depends on meta storage, which is etcd. It usually becomes a bottleneck as the cluster growing. And there are 2 famous things on Twitter. The first one is the order landscape at CNCF. And we can see that there are hundreds of projects in CNCF community. And the second one is revealing that all cloud native infrastructure is built based on a fragile etcd, a metadata storage. And this is the architecture of etcd. And in the following, I will introduce the issues we encounter in etcd. And as the scale increase, the storage system usually become a bottleneck. And the official recommended scale is 5,000 nodes in a cluster, which I think we have encountered a lot of issues when we increasing to 5,000 scale. And etcd is a leader for architecture. It has a leader to serve like write and watch requests, and followers of the read request. Include the API layer and the rough module and state machine and multi-version concurrent control and bot DB as a in-tree storage engine. And in API layer, we found that the etcd API layer is not good at rate limiting, or it usually cause thundering herd when you try to release the data, like when you list all the pods in cluster, it will cause some thundering herd. And in multi-version concurrent control, it will usually cause out of memory when you send some expensive read request to the etcd, and you also have a high latency due to the paging reading. And for the Raft module, we have encountered some bottleneck when you have a high rate QPS. The latency of single Raft group will limit the throttle the writing request. And finally, for the bot DB, the write performance limitation also we also encounter some limitation on write performance. And when the ETC is under a high load, we also meet some high write latency. And at the same time, it's pretty hard to defrag bot DB online when you try to defrag, and you will have a high latency for Kubernetes. And for here, we have two ways to resolve all these issues. The old way we have tried is to try to turning the parameters of etcd and try to replace some faster hardware for the storage, and we also try to split the object, like split the event object to another etc cluster to improve the performance. But after all this trial, we found that we still will encounter with some bottlenecking someday in the future if the business keep growing. So we try to try a new way to design a Kubernetes friendly metadata storage.
So Zheng, before we jump into the KubeBrain solution, we have already tried many other optimization solutions, right? We try to optimize some of the API server part, and we try to improve the watch performance of the API server, do a lot of like tuning, but we still find that the root cause is from etcd. So if we wanted to keep scaling up like to the 10,000 nodes, do these small tricks like tuning the API server or other components will not help. So we decide to go with a solution that can help us to resolve the problem from the bottom, right?
Yeah. And actually, etcd is designed 10 years before Kubernetes. So actually, it's not totally designed for Kubernetes, right? It's Kubernetes choose etcd as a metadata storage, and so maybe we think we are thinking if the etcd is the best storage for Kubernetes, maybe probably we can design a Kubernetes friendly storage. Yeah, it will be a better way to scale, to help us to scale up to 10,000 node scale.
Yeah, right. Yeah. I also noticed that a lot of people have tried a lot of things, try to resolve the scalability issue, but they finally run into the etcd problem. Yeah, so yeah, it's great to see that right now we have a solution that can help to resolve this root cause. Yeah, great.
One quick question: are you guys running your own Kubernetes distributions, or are you using a managed service?
We are running modified Kubernetes modified version in internal environment, not a community distribution.
Got it. Thank you for that.
But I think there is no need to change any other components if we wanted to use KubeBrain.
Yeah,
I think someone asked the question in the chat. So yeah. So
yeah,
no need to change. Yeah.
I will explain this part later.
Okay. Cool.
Okay. And KubeBrain, actually, KubeBrain is not an idea. Just jump into our brand. We dropped its inspiration from another project from Rancher. Rancher is a great company. Yeah, and the project is Kai. And what does Kai do? What does they do in Kai? And they implement a subset of ECC API. They don't because we know that it's not usable at all for general purpose in ECC, and they translate the ECC transaction calls into the design API like create, update, or delete, and it adapts to different backend driver, but most of driver, all of drivers are based on like relational database. So for us, we try to implement some similar stuff like Kai, but we choose a key value storage as our backend. And at first we can let's analyzing what's the requirement, storage requirement for API server. Actually, in addition to basic create, read, update, delete, which is CIUD, we also need like the single key conditional updating, and so the underlying storage must support like compare and swap semantic, and we also need the snapshot rate because Kube API server implements API trunking to support data paging reading.
Okay.
And as well, we also need watch API support, which is very important in API in Kubernetes API machinery, right? All the components interact with list and watch mechanism. So we need to,
so what's the major difference between like Kai and the KubeBrain, except the backend storage? Kai is using the SQL database, KubeBrain is using the KV store. Yeah.
Yeah,
so,
I think
it's just an extension of that question, right? Is KubeBrain acting like the orchestrator as in just a driver for the KV, or what is the exact goal of it? Maybe you can expand on those also. What exactly is doing in the middle, right?
Oh, what does KubeBrain exactly do, right?
Mm-hmm. Yeah,
I think it's pretty similar to Kai, and we just implement the API, the API servers needed, and like translate the API request to a key value storage request, translate the API, and and we optimize the performance for the large scale cluster. I think that's what we have done in KubeBrain.
So when I look into the Kai source code, I found that there is a major problem, or maybe that's not a problem, but sometimes when you try to do watch, if you are familiar with Kubernetes, we usually need to do a lot of like list and watch. So when we do the watch in a Kai, when I was looking at the code, I'm not sure if they changed yet, but when I was looking at the code, they try to do the keep polling the database. So that can cause a lot of like overheads. If you keep polling the object, you try to watch, right? So I think another major difference between KubeBrain and Kai is we are not going to pulling data, right? We are going to maintain the watcher inside memory, inside the KubeBrain. So that means if we successfully write something to the KV store, the response come back to the KubeBrain, we know that. And then we broadcast the events to all the watchers. So we largely release the pressure from the backend storage engine. I think that's just another contribution of the KubeBrain. Yeah, and there are many more. I can't remember, but KubeBrain do a lot of like optimization from every aspect: read, write, delete, and listen and watch. Yeah.
Thanks
so one of the problem that I've seen with like most of the cloud native operators, right? They store a lot of CRDs inside Kubernetes, and at some point the CRDs won't scale. Do you think with this the scaling of CRDs will be easier? Do you have any stats there on that? The custom resource definitions objects inside Kubernetes, like some people using Kubernetes CRDs as a database, right?
Correct. Totally.
Database won't scale beyond a certain point. So those kind of problems, will it be solved with this?
I would say somehow we can solve this problem to some extent, right? I think you have read I'm not sure. Have you read the article? I think it's published by Crossplan on Hacker News maybe 2 weeks ago. They mentioned a lot about when they try to use the API server to do the CRD, to manage the CRD, then they have a huge amount of CRD and how the API server and etcd run into the problem and how they solve them to some extent. But I think if they can combine it with KubeBrain, then they can scale to the next level. Yeah, if they have tens of thousands CRD, they can still handle.
Yeah, and actually, for Kind, they are designed for a different scenario with from us. Kind is designed for K3S, for a small. They are focused on like to use the less resource. So they choose SQLite as the first search engine, and because SQLite costs very less resource. But we are designed for a large scale.
That make a lot of sense. So as Zheng just mentioned, the Kind is used for a small cluster. If you are familiar with K3S, so they are used for a small cluster. So the cluster is small, so there will be less objects stored in the backend storage. So even though you pull the backend storage frequently, that will not cause many problems. But in our case, or in TikTok's case, we have a large cluster, have tens of thousands of nodes, and maybe millions of objects stored in the metadata store. So we cannot do just busy pulling the backend storage. Yeah, that's another major difference. Yeah,
it's a great point too when you compare like a production grade Kubernetes cluster and something like K3S, which I believe before it was GA, it actually released with replacing etcd altogether with SQLite or MySQL. I can't remember which one it was, but it was to reduce the overall distribution size, right? To be something that could run locally or in a CI context with high efficiency without all the maybe other moving parts that come with a full production grade Kubernetes deployment. So yeah, it definitely feels like Kind and so if they abstracted out Kind from what their original model was into something that is an add-on, a bolt-on, it was originally designed for that much smaller use case. KubeBrain seems like something that is designed specifically for large-scale production-grade workloads and not something that's stripped down, slimmed down version of Kubernetes.
Exactly. Yeah.
Cool. Is there any metrics around the number of nodes it can support? Like, I'm interested to learn. As in, is it? Are we looking at 1,000? Are we looking at 5,000? Any metric?
Yeah, I think Zheng, maybe you have some number in the following slides to show the scalability.
In the third part, we will share some performance, some benchmark data, and some practice we have done in TikTok.
Okay. So yeah, let's try to see what's the main idea of the KubeBrain.
Due to the time limitation, so I will not share all the details, all the optimization we have done in KubeBrain. I just will pick up some highlights. Okay. And yeah, we have 4 layers, and I will go through from the bottom to the top, and at the bottom is the storage layer, and then logical layer, and API, and the client. And for the storage layer, yeah, we define a unified storage interface, and we implement the different adapter for different storage. Like for ByteKV is the internal key value storage we use in TikTok, and TiKV is open source key value storage.
A graduated CNCF project at that, so high value, high quality.
Yeah. Yeah. And this is the this picture is the architecture of ByteKV, but it's pretty similar as TiKV. And I don't want to deep dive here, and Charles will bring us introduction later. And it's also support like multi-rough group or the in-global hypertext and blah, 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 blah. Okay. And then we can see the, let's go to the logical layer. And in logical layer, we implement these 4 major functionality in this layer. And the first one is how to encoding the key. And then it's the time step oracle, and leader election, and finally is watch events. How we implement the watch API for the Kubernetes. And KubeBrain use distribution key value storage as the underlying storage engine, which needs to store the Kubernetes data on a pure key value structure while ensuring high performance in read and write. And in etcd, both DB is used to store data, and the B tree in memory acts as an index. According to the B tree in memory, all version of a key can be quickly found and located. And for KubeBrain, the data also needs to be stored, include 2 parts. The first one is data, which is a key value pair, and the second one is index. They are used to help us to improve query performance and ensure the constraint. There are 2 patterns for query. The one is like query a row of data, which need to quickly locate the key value pair through an index. The other is a range query ish. And the range query will return a massive of data from the storage engine. And so, after the
yeah, so you encoding the key on this format. Is there any specific reason, like we have a same prefix for all these keys?
Yeah, sure. The prefix is to make sure the key was arranged together, because the underlying storage is in order.
I see.
Yeah, they order the.
Yeah, I see. I got it. So yeah, so that means because in Kubernetes we usually need to list a lot of like objects. They are under the same namespace, and like same resource, like the pods under same namespace. And if you wanted to list the 100,000s of pods, if they have the same prefix and store in the same spots, then that can highly improve the efficiency of the list, right?
Yeah.
Great.
And yeah, and we also in the key encoding, we also have a field we call it split key. That help us to make sure the index and the data was located in the same partition in the underlying storage engine. which help us like when you try to querying a key value, and you can make sure that will not become a distributed transaction call. Otherwise, it affects your performance, your throughput. Yeah, that's well designed for the underlying storage engine.
I see. Zheng, why not let's just see some data, like what's the scalability, the largest scalability we can support by KubeBrain?
Okay, I think the time is and that's the performance. Yeah,
we're going to be able to link the documents right to the meeting afterwards. So for what we've glazed over quickly in the support time, people have access to it after the fact.
Yeah.
Okay. Sure. We will share the slides after the meeting. Yeah. And okay. And for the, I'm sorry, I forgot to translate this picture. And the title of the picture is concurrent, the throughput of concurrence, and in the left is for pure write workload, and it's 10 times throughput of etcd for the write benchmark, and for the GET request, we have 20% increase in throughput of single key read, and for the range request, we reduce range request. We test in the least latency of 20 gigabytes data, and it reduced from multiple minutes to 10 seconds versus etcd. Yeah, and for the hybrid workload, the throughput is 4 times of etcd.
Great, that's impressive. That's very impressive data.
Yeah, and and the practice we have done in TikTok for the benchmark cluster, we have some internal API server optimization, but and with the optimization, the scale is up to like 50,000 nodes and 2 million ports in a cluster. And for our production cluster, we have scaled up to 18,000 nodes, and it's on the uptrend with the peak write request reaching more than 10,000 query per second. Yeah, I think that's the data we have. We can share so far.
That is high scale for sure.
Yeah, and we just mentioned that the internal optimization, but without the internal optimization, like we also can reach the like 18,000 nodes. But what we have done is in the internal change is we optimize the range and the watch request, like use when you try to range the data, we try to like query the underlying storage in concurrence. Yeah, but we are in the future work, and we are trying to make it we'll make it in the community distribution, open community distribution Kubernetes.
Yeah. So yeah, I know that the KubeBrain just open sourced. Yeah, and it currently just support TiKV, but maybe in the future we can support some other database or other backend storage, right? That's part of our future work.
Yeah.
Okay.
And it's open source. It looked like you guys had an appropriate interface of abstraction. So those that are interested that would like to plug it into another backend key value store, it sounds like you guys accept pull requests, right?
Yeah.
Awesome.
Okay.
It's impressive.
Okay, and this is the the word cannot see here, and the left QR code is for the KubeBrain GitHub link, and for the left is the hiring app. Yeah, you can scan that to reach us.
Awesome.
Okay, and that's all today. And any questions for you guys?
So I have a few. So does it work with K3s?
Yes, I think it works with K3s. It works with any standard Kubernetes release. Yeah.
Mm-hmm. Okay.
But you may need to tweak, because I'm not familiar with K3s. I'm not sure if they change anything in the control plane, but if they still follow the standard Kubernetes API, then totally fine. It can work with KubeBrain, no problem.
Yeah, yeah. What I want to share is actually at the very beginning we didn't change any code in Kubernetes. We just use the etcd client in the API server and just to call the KubeBrain, and that's totally good. And after that, we are trying to implement a client, a KubeBrain client in Kubernetes API server, and a native client is better supported and optimized for a KubeBrain.
Mm-hmm. Okay.
Okay, Charles, let's, sorry, Chakri, unless it's a burning question, maybe we could save it to the end, but I want to make sure Charles covers his material.
Okay. Yeah, sure. I can also answer some of the KubeBrain's question because I am also a maintainer. So yeah, we can try to answer the question by the end of my talk. Yeah.
Awesome.
Yeah.
Awesome.
Cool.
So great. So I am going to share my screen. I'm trying to share my screen now. And
all right, Charles, look forward to it. Yishin, thank you very much for the presentation.
Thank you, Mike.
So could you see my slides?
Yep.
Great. Okay, so can I get started or?
Yep.
Yeah.
Let's go.
Go for it.
Okay. Give me 1 second. Put out. Okay, so thanks Yishang's talk, and I will try to take over from here. I'm Charles, software engineer from PingCAP. So as Mike was mentioning, I have been working on Kubernetes and cloud native technology for almost 5 years. I assume most of you, like me, have some experience with Kubernetes and cloud native technologies. So even though I'm going to talk about distributed KV store, but I will try to cover the rest of this talk from a cloud native engineer's perspective. So in the previous talk, Yishang has already mentioned that the TikTok faced some challenges when they try to scaling up Kubernetes to over maybe 10,000 nodes, and how KubeBrain address all those challenges. But as the storage service, KubeBrain needs to be run on top of the storage engine. And the TiKV is recommended as the default storage engine for the open source version of KubeBrain. So why KubeBrain choose to use TiKV as the backend storage engine over other options? That is the question I will try to answer in the rest of this talk. So here's an outline of my talk. First, I will do a very briefly recap. So part of the previous talk and summarize the major requirements for metadata store of large scale infrastructure. And then I'll give a high level introduction to the overall architecture of TiKV, which can help you to better understand the rest of this talk. And after that, I will elaborate how TiKV meets the 4 requirements. And finally, I will extend the talk a little bit to explain why TiKV can not only be a solid building block for metadata store, but for all other distributed or higher level servers. Okay, so let's get started. First, let's recap a little bit. So what are some requirements of KubeBrain for the backend storage engine? Here is what I found in KubeBrain's GitHub repository. They are many, right? And they are just the partial requirements for data consistency. There are many other requirements regarding to scalability, fault tolerance, rewrite throughput, etc. But in general, we can divide them into 4 categories, which is to say the backend storage engine should be first, be highly scalable. A large Kubernetes cluster may contain tens of thousands of nodes, hundreds of the pods, workloads, or any other informations. This can result in millions of entries and gigabytes of data, which require the backend TiKV store to be very highly scalable. Second, we need to ensure the data is consistency. If you are familiar with Kubernetes, you may notice it is very common that there are hundreds of controllers, operators, or clients try to access the cluster at the same time. So it is very important that we allow all these clients or controller to watch same group of objects in the same sequential order. For example, if we develop an operator watching stateful set and its relevant parts, then it will be very weird if we found that the stateful set is ready prior to the relevant parts being ready. Third, we need to support high performance I/O. If we have hundreds of clients try to access the cluster state at the same time, it will be critical that they can get response within a very short period of time. In addition, Kubernetes is famous for its least watch pattern. So writes could also need slow writes could also lead to long watch latency that can largely affect the performance of critical system components, like the scheduler. So scheduler watch all these parts. So if we update the path states very slowly, then the scheduler will get the latest path states in a very long period of time. That can further reduce the scheduling throughput of the whole cluster. And the fourth, be extremely reliable. So Kubernetes follow the classic coordinated worker architecture using a central control plane to manage the whole cluster. So as the brain of the control plane, the fail of the metadata store can result in losing control of the whole cluster, which is intolerable. Next, I will try to elaborate how TiKV meets all these requirements. So before that, let me briefly introduce the overall architecture of TiKV from high level, and hopefully it can help you to better understand the rest of this talk. So TiKV is a distributed transactional user-friendly key value store. And hopefully by the end of this talk, you will agree with this statement. A TiKV cluster looks like this. The storage nodes are on the bottom. You can have as many as you like, but we usually suggest to have at least 3. We split the data into regions. We know the name is confusing, but you can just treat a region as a subset of the data. As shown in the graph, we split the complete dataset into 5 subsets, which are 5 regions. Each region contains multiple replicas, which are spread across different TiKV nodes. In most of the case, 3 replicas should be enough. On the top, we have the TiKV client communicating with the TiKV clusters through the gRPC protocol. And on the top right, we have the placement driver, my favorite part, which is the scheduler of the TiKV cluster. The placement driver has 3 major jobs. First, generate a global monolithic and a unique timestamp for the transaction, which can also refer as the TSO. Sometimes people like to use the term timestamp oracle, but I feel it's very confusing. So let's stick with the TSO. Second, manage all the data region across TiKV nodes, like rebalancing regions, migrate region from offline nodes to active nodes. And the third, since the placement driver store all the metadata of all regions, it will also be responsible for routing read and write requests from clients to correct nodes. Okay, we have seen how TiKV looks like on cluster level. Next, let's have a look at how TiKV implemented internally from the node level. So each TiKV node can be divided into 4 layers. From bottom up, we have the storage engine, which is a low-level local key value store. And we choose to use the RocksDB. We leverage this layer to perceive the data into the local file system. We did not implement the local key value store from scratch by ourselves, as implementing a high-performance local key value store requires a lot of efforts, and RocksDB has been proven to be reliable with predictable performance in production by many data management systems. One level up, we have the consensus layer. This layer presents the abstraction representing multiple replicas, which allow upper layer to feel like that they are dealing with just one piece of data instead of multiple replicas. So like etcd, we use the wrapped consensus algorithm to ensure the data consistency between replicas across multiple TiKV nodes. But different from etcd, we use multi-wrapped group instead of single wrapped group to improve the scalability and I/O throughputs, which we will cover in following slides. On top of the consensus layer, we have the transaction layer. We use the multi-version concurrency control to implement the Google Percolator protocol, which commits transaction using the two-phase commit algorithm. I know a lot of database terms, right? If you feel like it is a little bit too much, that's normal. It is not easy for a database expert as well. And from my opinion, the distributed transaction is one of the hardest part to understand in a database management system. But fortunately, TiKV has already implemented and we can safely rely on it. And on top, we have the key value API layer, which is responsible for handling requests from the client. The API is quite generic: get, put, delete, scan. If you have ever used any other key value store before, then I think you can pick it up very quickly in maybe just 10 minutes. Okay, so now we have enough background and I can start explaining why TiKV can be a perfect storage engine to store large volume of metadata. So first, let's try to figure out if TiKV is highly scalable. One of the major difference between TiKV and etcd is data sharding. So in TiKV, we divide large data sets into small regions, with each region containing several replicas making up their own wrapped group. The number of replicas may change depends on how TiKV nodes are spread geographically. But in most of the cases, each single TiKV node does not need to store the full copy of the data. That is to say, TiKV is horizontal scalable. When a volume of data is increasing, we can simply scale out the TiKV cluster by adding more nodes. In contrast, etcd does not support sharding, and each member nodes need to store a full copy of data, which means when a data volume reaches certain size, the scale out becomes meaningless. You may be curious, if each node does not have a complete copy of the data, then how can we tell which node should we access if we wanted to read or write certain entries? If you remember, we have a central component called placement driver, which will act as the scheduler of the TiKV cluster. As replicas of each region making up their own wrapped group, the leaders of each group will hold the complete information of the region, like the number of active applicants, the topology of the applicants, and the leader of each group will send heartbeat to the placement driver periodically, including all this information. Then, when a TiKV cluster receives a request from a client, it will first query the placement driver, get a target node, and then route the request to the node. The placement driver also supports users to create highly customized configuration like maximum number of replicas in each regions. How can we balance the leader across nodes and the scheduling throughputs? Because too much data migration or balancing during the runtime can affect the performance of online servers. So to sum up, by breaking up the data into partition and spread replicas of the partition across nodes, a TiKV cluster can be easily scaled out to hundreds of nodes. Here are two large real-world TiKV clusters. The left is one of our user suites. So it is a TiDB cluster backed by a large TiKV cluster, consists of 168 nodes with 1,820 billion rows and 300 terabytes of data, which need to support 100 million reads and 87,000 writes per second. The user thought it is the largest one, but soon we had a larger one, which contains 200 nodes and can hold up to 800 terabytes of data. We have not tried yet, but we did not experience any pressure with this cluster, so I believe we can easily grow larger. Okay, so now we met a scalability requirement. Next, we need to ensure the data consistency. When we are talking about the data consistency of the distributed database system or data store, we usually need to achieve two goals. One is isolate transaction from each other. Another is keep the data consistency between replicas. These are two complicated topics with a whole session to discuss, and we do not have time to do that today. So let's try to make it simple. In short, transaction is just an operation unit containing multiple operations. For example, if we wanted to update a parts, we'll normally need to first read these parts from the backend storage, right? And we'll update these parts spec based on the existing value, and we will write it back to the storage. That is an example of a transaction because it's including two operations, read and write. So, but at the meantime, also we have to store the replicas for each data partition. So we need to make sure the contents of each replicas is consistent with each other. As we can see in this graph, the left subtree contains different transaction isolation level, and the right subtree contains all the local object consistent model. If you still remember, TiKV internally contains 4 layers, and in the middle 2 layers are the transaction layer and then the consensus layer. And then the transaction layer ensures 2 things. One is the snapshot isolation, which means we create an independent, consistent snapshot of the database for each transaction. It's change our visibility only to the transaction until the commit time. This allows us to handle transactions concurrently if they are not interfere with each other. Another is the repeatable read, which means any data read cannot change. If the transaction reads the same data again, it will try to find the previous read data in place unchanged. For example, if you read a specific version of a pod first, and later when you read this pod again, you may find that even though there may be some new versions of these pods, but the previous version you read is still there and unchanged. Also for the consensus layer, we use the route consensus protocol. So like etcd, TiKV ensures a strong consistency, which is also known as the linear realizability among replicas of each object. I know these slides may contain a little bit too much database terms, but for now, you can just remember that the date consistency provided by the TiKV is as strong as the etcd. The next requirement we need to meet is the high performance I/O. For the read, as we use the multi-version concurrency control to implement 2-phase commit, which means we versioning each key value pair and create isolation snapshot for each single read and write, which prevents a read request from being blocked if there is an ongoing write on the same entry. We also apply many other optimization approach. For example, we support follower reads that allow us to spread the read workload across all replicas, or we prioritize small reads to prevent overall throughputs being affected by several large reads. On the right, since we divide data into partition, with replicas of each partition make up their own raft group, then write requests on key value pairs belonging to different partitions can be handled concurrently. We also try to optimize the write performance on the local storage engine level by developing a RocksDB plugin called Titan. Even though RocksDB provides very good or predictable performance, but since it is based on the log structure merge tree, so it can still suffer from the write amplification. So the basic idea of the Titan is we are going to store large value outside of the SS table, the log file. So this helps us to avoid the write amplification caused by the RocksDB. And for the scan, since we do the range-based sharding that divides data into continuous range determined by the shard key, scanning keys sharing same prefix can be very efficient since they are usually located in a handful of regions. This is especially useful for Kubernetes. So as I was mentioning, when we are using Kubernetes, we usually need to list a huge number of resources under the same namespace. So since all these resources, they are sharing the same prefix. So if we organize keys by the key range, then this list operation can be highly efficient. Besides all these, we also apply some configurable optimization features, like we can enable the load-based splitting on placement driver, which will split the hot region if it receives a lot of a read-write request. Okay, so here is what people are asking. So here is a basic benchmark. So we compare just the 3 nodes etcd versus 3 nodes KubeBrain plus TiKV. So remember, we only compare 3 nodes. So you can find the detail of this benchmark on the KubeBrain's GitHub repository. So in this benchmark, we try to compare 2 kind of operation. One is insert and read. We'll insert something into the data into the metadata store and try to read it. The second one is just insert. So as we can see that The x-axis is the name of the operation. The y-axis is the throughput. So KubeBrain plus TiKV outperform etcd from every aspect, which has 3 times higher read and write throughputs. You can find, and you can also find more other details on KubeBrain's GitHub repository. But we only compare 3 nodes. So if we scale up, if we have huge amount of metadata need to store, then we maybe need to have 10 nodes or even more. Then KubeBrain plus TiKV can have even better performance than etcd.
Charles,
Okay.
I want to stop you there just because it's not driving me nuts, but it's like making me very, very passionate. So as we are scaling out, we have a hybrid cloud, and we have both public cloud vendors, and we have internal on-prem private cloud environment.
Yes.
How does KubeBrain plus TiKV scale to both the public cloud vendors, right, where we've got the control plane is typically the managed part of
Correct.
the managed service, and then in addition to that, there are the availability zones, right? So how does it scale across availability zones, where those can, I think in traditional data centers, those would be considered regions in the same region. So can you elaborate there, Charles, please?
Yeah, that's a very good question. So let's assume that KubeBrain or plus TiKV has been adopted by some public cloud to manage their control plane, and KubeBrain and TiKV can actually help them to improve the high availability of the whole control plane, because we can spread the TiKV nodes across multiple available zones. And if you remember, we have a placement driver. That one is actually the topology awareness. So in each zone, each TiKV nodes, the TiKV nodes in each zone will have a complete copy of the data. So for example, in a very bad scenario, if one of the zone down, one of the data center down, but since we have the TiKV nodes on all other available zones, so this whole control plane is still available. So we can largely improve the availability of the whole control plane. Yeah.
Got it. Okay. And then in the availability zone, like let's just say there's 3, you've got multiple dozens of nodes, right? In your use case, I think you guys said like upward 1,000 plus, right? So in that case, the availability zone goes down, the RAF consensus algorithm, a new leader will be elected, and you'll have multiple replicas or copies in 2 other availability zones. So there should be a no op, right? From a AZ being down.
Yeah, correct. That's correct. Yeah.
Awesome. Thanks.
Okay.
So do you know of any public cloud vendors that have picked this up or have made it something that is available for clients to leverage?
I think it's right now, if just KubeBrain plus TiKV is still like the KubeBrain is just open sourced. So we try to push forward this whole project. But for TiKV itself, it has been deployed. It has been used by many users. They have already proved that TiKV can be highly reliable if we spread them across multiple available zones. Yes.
Yep.
Okay.
Awesome. That's a good distinction. So TiKV, mature, graduated CNCF project, and everybody knows that's a high bar to achieve. KubeBrain just open sourced, leveraging TiKV on the back end as its default key value implementation. Thank you very much. That's great clarity.
Okay, great. Okay, so the last requirement, let's finish this talk. So the last requirement is the TiKV need to be extremely reliable. So, so for the extremely reliable parts, we have provide fault tolerance. So as what Mike just asked, so if we deploy the TiKV on the cloud, we can actually spread the TiKV nodes across multiple available zones to increase the high availability. And also for the disaster recovery, in a worst case scenario, if you really just lost on the nodes, we provide some tools that can help you to recover the cluster from the failure, right? And also, TiKV is very well tested. So we run regression tests to ensure the new features is backward compatible and will not break the historical release version. We also run large multi-day performance tests that use real-world data to ensure the performance is predictable. since many users adopt TiKV as the backend storage engine to build their own software as a service product, predictable performance is critical to make service level agreements or for higher level servers. So if you are familiar with Jepsen organization, we run several open source Jepsen tools to make sure TiKV to ensure to deliver the transaction promise we have made. And also we do chaos engineering with Chaos Mesh. If you are not familiar with Chaos Mesh is another project initiated by PingCAP and has been donated to CNCF as an incubating project. It allows us to simulate unexpected situation like nodes going down or network breaks and so forth. So as we can see, TiKV is highly scalable with strong data consistency and good I/O performance, which makes it a solid building block for not only the metadata store, but also for many other higher level servers. But you may be curious for what reason we built up the TiKV at the first place. So we start building, so we are a database company, we call PingCAP, and the most famous software we built is the TiDB. The cloud native database support both OLTP and OLAP workload. But back in 2015, when we built up the first generation of TiDB, we built it up on HBase and HDFS. So if you have ever dealt with Hadoop software stack, you may have the same feeling that they are not easy to work with. In addition, as we want to develop a database support distributed transaction, then we have to add distributed transaction support on top of the HBase, which cause poor performance and high operation cost. After suffering enough, we finally decided to build our own storage engine with following requirements. So first, it needs to be easily scale out, like all other NoSQL database. Second, it should support high performance I/O. And third, it should support transaction inherently. Fourth, it should use modern data replication protocol like Raft. Fifth, we wanted to make sure it is very easy to maintain. So it has a clean architecture. And last but not least, it should be easy to use. Anyone who uses other key value store should be able to pick it up very quickly. So from the day one, we decided to develop a storage engine that can be a solid building block for other distributed systems and really help people out. And this principle can also be applied to all other software from PingCAP community. So our founders always tell us that our goal is to build good infrastructure software that can be easily embedded into other systems and help them to scale. Okay, so I think to some extent we have already achieved this. Besides KubeBrain, TiKV has been adopted by many famous distributed systems. So I just list some of them. The first one is SarioDB, a cloud database for modern application, which is just open sourced recently. And Zeta, the open source NoSQL database, TDs, a distributed NoSQL database compatible with Redis API, and Titan, another Redis implementation using TiKV, and the Juice file system, and open source POSIX file system based on TiKV and the S3. Okay, and also with the help of TiKV, our dream come true, we largely improved the performance of TiDB from every aspect. Here is a fresh benchmark result from TileBench paper by UC Berkeley, published on VLDB 2022. This benchmark compares several mainstream cloud-native databases. The first row shows the performance on medium datasets, and on the second row shows the performance on large datasets. As we can see, compared to other cloud-native databases, TiDB has better performance on both read and write transaction and can support large datasets. So TiDB has been trusted by more than 2,000 companies and organizations from different fields, including several top techs in the United States, that prove that TiKV can be highly scalable because big tech companies usually need to handle a large volume of data. And 2 out of 3 top cryptocurrency exchange company, which proves that TiDB is very reliable and secure. One of the top 3 largest bank in the world, which proves that TiDB provides good data consistency and a strong isolation between transactions. So cooperate with all these partners and many community members. We keep improving the performance of TiDB and never stop evolving. So thanks, that's for today's talk. So all the software mentioned in this talk is fully open sourced, including all advanced features. So feel free to try them out. If you have any questions or comments, please shoot me an email, or if you are in the Bay Area, you're welcome to stop by our office. We can grab a coffee, and I would like to discuss any topic related to database or Kubernetes with you. All right, thank you.
Thank you. So I think we have time for a few questions. Charles, there's one in the Q&A box there. Take a look at that real quick. And then Vinkat had a question from earlier, but maybe take that one in the QA real quick.
Okay, let me see. Okay. So is it Kubernetes cluster is large in ByteDance deployed across region, and if so, does the metadata store also cross regions? Yeah, I think that is a question for Yishang, because yeah, I'm not familiar with internally in ByteDance.
Actually, we don't deploy the Kubernetes cluster across region. Yeah, we only in our architecture we will deploy the cluster in data center. Yeah, and it may include some availability zone, but we will not do it across the region.
Okay. Yeah. Yeah, I think, is there any other questions? I think that's the only one I saw.
Chakra, you had a few questions from the previous presentation, right? You're with it, or?
No, I think mostly around the high availability for the KubeBrain, right? So I'm assuming KubeBrain is not a single point of failure. It has high availability built in. Is that right?
Yeah, I think so, because KubeBrain for an open source, for example, is leverage the TiKV. So TiKV itself is highly reliable, highly scalable. So yeah.
Understood. So, but the API server talks to KubeBrain, and then KubeBrain talks to TiKV. So the KubeBrain itself, is it highly available?
KubeBrain itself, I think we have multiple server, like what we deploy other workloads in Kubernetes, right? We normally will have multiple replicas for each pods, for each service, right? KubeBrain, I think it's shared the same principle. Is that right, Yishang? Is that correct?
Yes.
Yeah. So even though we may lost one of the pods or replicas, but it will do the leader election. So I think the interruption time will be less than 10 seconds normally. Yeah.
And maybe, Charles, we can follow up with some documentation on that, maybe.
Oh yeah, sure thing. But yeah, I think you can find some data in KubeBrain's GitHub repository, and I will try to share some of this documentation after this talk with the slides. Yeah.
Awesome. Go ahead, Chakri.
Yeah. So if we use KubeBrain, then you would not need etcd. Is that right?
Yes, I think so. Yeah, if we wanted to use KubeBrain, then we need to migrate existing cluster if the cluster is using etcd to the KubeBrain. But in some case, I mean, I think we can also use etcd as the backup storage of the KubeBrain. So for example, if we have a KubeBrain as the primary metadata store for the cluster, and we can at the same time has a etcd as a backup storage for the whole cluster for the metadata store.
Okay. So I'm assuming KubeBrain is running as a process on the host, not as a container, right? Like I see the documentation. Yeah, I think there's a lot more documentation coming in, but the way I see it is it's running as a process on top of the host, right?
Yeah, for now it's a process, but I think we can containerize the KubeBrain. We can deploy it as a independent container. I didn't see any like blocker for doing that.
Yeah. KubeBrain actually is a stateless application, so I think it's pretty easy to containerize it.
Yeah, I think that's a very good action item. We can try to make it containerized and easily to deploy it. Yeah.
Okay. Yeah, I'm really confused because which comes first, right? Like if KubeBrain cannot come up without the etcd, and like it will be a chicken and egg problem. I don't know. I may be missing something, but I'm trying to wrap my head around, because the API server requires some storage backend, and KubeBrain is the one that is replacing that.
Yes. Yes.
So
correct.
how it will not function if it is a pod. So yeah, okay. I'll just watch on the KubeBrain GitHub. See.
Okay.
Yeah.
Okay. Great.
Awesome. So maybe one last question and we'll wrap it up. Venkat, I wanted to give you a chance. You had a question earlier. I don't know if that's still a question for you. You mentioned to what degree the complexity was reduced. I think that was earlier when Ishwan was having his presentation.
I think it was answered in the later slides.
Was it answered? Okay, cool. Okay, guys, I think that's it. Mike, did you have any parting thoughts?
Nothing outside of like the, you know, if you enjoyed this talk and the other ones that you've been a part of, the YouTube channel for Cloud Native at Scale, go smash that bell and follow. And Eventbrite is where all the events are published. Charles, Ishian, it's just been great. Really appreciate it. Super technical, and people can connect with you offline. And thanks again for the time today, everybody that's joined and everybody that's presented.
Yeah, thank you. And then Mike, I want to thank you, and I want to thank BlackRock for helping to get this out there. We really, really appreciate your support for our community. So thank you, everyone. Look, great, Chris, to see you, and a lot of familiar faces. And we'll send out the recording and the presentation and all that good stuff within the next couple of days. Okay, everybody, thank you.
Amazing.
Thank you, Josh.
Thanks.
Thank you. Welcome.
Thank you. Bye-bye.